at the Large Hadron Collider at CERN, we build what's essentially an enormous microscope. The bigger you build the thing, the smaller you can get. So yeah, you basically smash small bits of matter together. You try and produce new particles that you haven't seen before, and then see how what happens is they decay into other particles, and you detect those. So it's quite indirect. I mean, you're producing some particles, they're decaying, and then you've got some big complicated machine that acts like a sort of three-dimensional electronic camera with lots of different components. And then you put it all, you take all the data, all the electronic impulses, you put it in a computer program, and you try and do some detective work to work out what was happening. But it sounds quite indirect, and you have to be careful. It's easy to make mistakes if you do it wrongly. So this is how the Higgs boson was discovered, for instance.
So you didn't actually see the Higgs boson?
Not with your eyes or with your ears.
Yeah. So how did the yourself and the other researchers working on that discovery, how did you know that you'd seen the Higgs, you'd observed the Higgs boson?
We made predictions with theory, with mathematics and the theory that we suspected was true, as to how the collisions should look like if the Higgs boson was there, and how they should look like if it's not there. And it turns out that the way it was detected was you look for you look for the cases where you produce a Higgs boson and then it decays into two particles of light. Only about 1 in 500 Higgs bosons decay into two particles of light. The rest go some other way that's more difficult to see. So you look at these, what you do is you do lots and lots of collisions, you filter out all of the other collisions, and you look for the ones that only have two particles of light with quite a lot of energy. If there's a Higgs boson, the energies of these photons, these particles of light, should add up to the mass of the Higgs boson. So you do get ordinary processes which give you two particles of light, and they have a kind of probability of being produced that just decays smoothly with their energy. So the high energy ones you don't produce so much, but the low energy ones you produce a lot, and it's some smooth distribution. But the Higgs bosons all come out with one particular energy. So what you're looking for is a smooth distribution with energy and a big spike in it, and that spike is your Higgs boson. Now, this sounds very indirect, and it is. And you're not sure that it's a Higgs boson if you just see this. But the Higgs boson makes other predictions. You should also see it decaying in different ways, which you can see less well, but you can predict how often you should see it, how many the collisions you should see it decaying a different way. And so you look for those and you try and corroborate all these different facts and see if the experimental data matches up with the theory, and it did in this case.
And so with that information, you were able to not only confirm that you'd seen the Higgs by matching it to the predictions of your theory and the experimental results matched it, but you're also able to measure its mass because of the energy of these two photons.
Exactly. And then you start measuring more of its properties. But I've got to say that there's some statistics that you have to do in this story that I just told you. Because what you do is, you do a collision, say you see two particles of light, they've got a particular energy, and there's and then so you say, okay, let's do another collision, and the energies come out random. This is a quantum process, so it's inherently, by the laws of physics, it's a random process. So you can't say on any particular collision what the energy is going to be, or even if it's going to give you two photons. But what you can say is, if we've got the theory right, we know what the relative probabilities of the different possibilities are. So what happens is, as you collect the data, initially it looks quite noisy. It's not some smooth distribution with a peak on it. It's all over the shop. So you can look in this data and see lots of peaks. And the question is, statistically, how likely is it that peak is due to something else than just a random fluctuation? So that's when you have to start doing some statistics, mathematics, and we have these kind of gold standards of how much it should stick out above the noise. in terms of these numbers of sigmas. But it's really about it's really a way of encoding the probability that you've got a big peak in the data just from random fluctuations.
So you need to be able to gather enough data to be able to pass these statistical tests to make sure that what you're getting is the effect that you're hoping to have observed.
There are two thresholds in particle physics that we use. One of them is evidence for an effect, which means it's interesting but we're not sure. And that happens if the probability of this peak is 1 in about 1,000. So in other words, you could do 1,000 Large Hadron Colliders with the same conditions that you've done, and only one of them, just by chance, would give you a peak so big, right?
Randomly from something.
Just, yeah, not from the Higgs boson, but just randomly. And then the gold standard for observation, this is a discovery, is about 1 in 10 million. So if you collect enough data, there's a peak that only 1 in 10 million times in this fictitious universe where you did it 10 million times, would you get such a big peak by chance? Then you say, okay, we're sure that's not due to chance. That's too smaller probability.